Good Saturday afternoon, guys. Hope you guys didn't get too much rain yesterday and hope nobody got flooded. Let's go ahead and look at our second video. We're going to call this the second part of kind of how scientists work. It's demystifying the nature of science because it can be kind of mystical. It's kind of a mystery in some cases. Got a bunch of learning targets, so you might want to pause this, take time to write them down. I'm not going to go over them. They'll be on the wall of the classroom anyway. So the other day when you did your experiment with the thumbs, I tried to show you the difference between the experimental group and the control group. When you do an experiment, it's got to be a controlled experiment, and you've got to have a control group to compare to, and you also have to have controlled variables, those variables that you do not want to test and you don't want them to influence the outcome of your experiment. So that's what control variables are, and you need to be sure you understand what the difference in the two groups are. So here's probably a brand new word for most of you. Inferences, or the process of inferring. This is what you do when you can't really see something happening, hear something happening. You see the instance of it. You see kind of like, well, let's just look at my example. I'm having trouble coming up with the words without using an example. So look at the fourth bullet, and it says here, you walk outside your house and you smell the strong smell of smoke. So your brain automatically registers, even though you don't see the fire, you infer that something's burning. So you do that based on prior knowledge. Okay, you do that based on kind of like, you might even want to say common sense. I don't want you to confuse this with a hypothesis. A hypothesis is usually followed up by an experiment, but not always. An inference is just you using prior knowledge to explain something. You don't have to try to prove it, just explaining something. Another example would be, let's say you're downstairs in a two-story house and you have a baby brother that's asleep upstairs in the crib. And all of a sudden you hear a thump, okay, and it's followed immediately by some crying. What do you infer? Okay, you infer that chances are your baby brother has climbed out of the crib and fell. You know, that's the thump and then the crying. So that's an example, two examples of inferences. A theory. This word gets so much improper usage. Theory is a bunch of data from lots of experiments, and it takes a long time to become a theory, but you take several hypotheses, and with enough proof and enough data and enough testing and enough peer review, if it stands up to those tests, then sometimes those hypotheses could be all rolled into something called a theory. Theories are not something that happen easily. And if you look in the third bullet, when somebody says, I have a theory about who shot that man, or I have a theory about who's going to win that ball game, or I have a theory about why we lost that ball game, you don't really have theories, you have hypotheses, or you have an inference even sometimes, or you have an explanation or an opinion, but it's not a theory. A good example in earth science is the theory of plate tectonics. No one's ever seen the plates move under the crust of the earth. No one's ever seen them move. No one's ever seen firsthand movement of the magma doing this convection current type thing, which we'll learn about later in earth science. But they believe this to be true, and they have lots and lots of data from other kinds of experiments to prove that and to back it up. So the name theory of plate tectonics was the word theory was slapped onto the idea or the hypothesis of plate tectonics many years ago. Scientific law. Sometimes we like to confuse or compare scientific law with scientific theory, and you shouldn't really do that. But scientific law doesn't require a lot of external proof. Okay, it requires basically just an observation, and the law of gravity is a pretty good example of this. You don't need to prove gravity. Okay, nature kind of shows it to us. A lot of times scientific laws can be expressed in a single mathematical formula. You know, like I got an example, the law of gravity. I can't remember the equation now. We'd have to ask Doc the equation for that. But you don't have to do a lot of work to show that a scientific law exists. Okay, two kinds of scientific research, or two kinds of science. Pure science is science for the sake of knowledge. You wonder some things, you make some observations, you piddle around a little bit, and eventually you do some experiments and you learn something from those experiments. That would be the pure scientific knowledge. Now, if you or someone else took that information and applied it towards something, and it generated a new drug, a new medicine, a new procedure, a new piece of equipment, that would be applied science. And a great example of that is the microwave oven. There was a guy who invented a device called a magnetron back in the 40s, I think. And this magnetron generates microwaves, microwave radiation. Someone decided to stick it in a metal box, put a dial on it. Later on, it became replaced with numbers. And now we call that a microwave oven. The guy who invented the magnetron, I don't think he had any thoughts of doing that, but somebody else took that information, took that science, and then applied it somewhere else. So let's jump straight into measurements now. And we're going to do some measuring in class. So I want to get you some basic information about units. Scientists measure in something called the SI system, which is short for the International System of Measurements. They don't use the English system. They don't measure things in feet and inches, in pounds and ounces. They measure things in like meters and kilograms and centimeters and things like that. It's kind of like the metric system. So if you call it the metric system, then I'm okay with that. So if you see on this chart, here's some basic units of measurement, or basic measurements. You can measure how long something is. You can measure the mass of something, the volume of something, the time it takes to do something, the temperature of something. So I've given you the very basic unit for each one of those. And then there's things called calculated measurements or derived measurements. Okay, sorry, I had to pause the video, so if you see a little glitch there, it's the reason the washing machine was out of balance and it was deciding to walk across the utility room floor. So I was saying calculated measurements, sometimes called derived measurements, here on the right side of this chart. The two we're going to worry with are area and density. And you don't really have a tool to measure that. Like over here, you can have a ruler to measure the length, or a triple beam balance to measure the mass. But over here, area and density, there's not one instrument. You have to take two measurements at least, sometimes more than that, and then do some calculations, do some math to come up with these numbers. So we're going to explore both of these in class. So what happens if you take those basic SI units like meter and kilogram and such, and then we change the prefix in front of the word? We add something like decimeter or centigram or milliliter, just to name a few. Here are the 6 basic prefixes that we're going to explore in class, and then here are their values, both using words and numbers. Okay, so I'll just go over one of them with you for an example. Centi, like centimeter. You know, centimeter is that length about this long. There's 100 in a meter stick. There's about 2.5 in an inch. Okay, its value is 1/100th, and so that's 1 over 100 as a fraction. So it's smaller than a meter. It's 100 times smaller than a meter. That's why 100 of them make a meter. Okay, so these new units, once you start combining those words, here's some example of what I just said: centimeter, millimeter, kilogram, decameter. That's not all of them. You can put any prefix in front of any measurement. All right, here's something a little complex. Now there's some examples in the next 2 slides, and you don't necessarily have to write the examples down, but you might want to stop it and actually work it out, work the examples out. And this will be something that I'll clear up in class. You're probably not going to learn this from the video, but you need to get some basic information down, at least on paper. Scientific notation. In science, sometimes there's some really big numbers and some really tiny numbers. And instead of using great big old numbers like this one I'm highlighting here, and this 90 billion stars in a galaxy, those numbers are sometimes hard to deal with because calculators are limited on their digits, and we're limited on our knowledge of really big and really small numbers and what they're called. So we can actually express these in something called scientific notation. where we take the number like 90 billion and we move the decimal. In this case, because the decimal is starting right here at the end of the 0, we move it to the left until what we have left, we move it until we got a single digit number between 1 and 10 left. So we're going to move that decimal to right here to the right of the 9. In that case, how many places did we move that decimal is the number of powers of 10 that we're going to express this number in. So we happened, if you were to count this, it would be 10 places to the left, and by moving things to the left, that's going to give us a positive exponent. So we would write the number 90 billion like this: 9 times 10 to the 10th power. 10 to the 10th power is a 1 with 10 zeros. So 9 times that would be 9 times 1, or 9 with times 9 with 10 zeros. Okay, so if you count the number of zeros here, 3, 6, 9, 10, that's where you have your answer. If you have to shift the decimal to the right, then that's like having a really, really small number and your exponent becomes negative. So if you see a negative exponent like negative 10, that's a really tiny number. That's so much less than 1, where this one is so much bigger than 1. So we'll do examples of this in class. And with scientific notation, you can actually multiply, divide, add, and subtract. We're going to worry about multiplying and dividing because that's the easiest. Adding and subtracting is a little bit more difficult, and I think you'll learn this in your math class, your algebra classes anyway. So when you multiply two numbers in scientific notation, you add the exponents together. You multiply the actual numbers, like here's an example: 3 times 10 to the second. By the way, that's 300. Times 10 times 2 times 10 to the fourth. That's 20,000. So 300 times 20,000, we multiply the 2 times the 3, that gives us the 6, and then we add the exponents. 2 plus 4 is 6, and express that as powers of 10. So 3 times 2 is 6, 2 plus 4 is 6, the answer is 6 times 6 to the 6th power. And that happens to be 6 million. So here that is written out here in the way you would do it with regular numbers. Now that's not a really big number. We could do that with regular numbers, but when we get to numbers like we saw in the last slide, the 9 billion, it's a little bit different. If you're going to divide two numbers in scientific notation, you simply, as you might figure it out, you subtract the exponents. So here's an example: 9 times 10 to the 5th divided, that's what that slash means, by 3 times 10 to the 3rd. It's going to give you 3 times 10 to the 2nd. Why? Because 9 divided by 3 is 3. 5 minus 3 is 2. So in regular numbers, it looks like 900,000 divided by 3,000. That's going to equal 300. Okay, that's it, guys. I'll see you in class on Monday. Please take these notes, especially if you didn't do well on that last test. Ask yourself, did you take notes? Then if you didn't, then that's something you need to start doing right now. Thanks. See you guys Monday.